Okay. uh, if it is R, then how do we define a sequence? Do you remember? Sequence is a function from natural number to Rn, correct? Is called sequence. So it is a function where domain is natural number, that's it. It's called sequence in Rn. Yes. And how do we represent the sequence? We represent like this. Suppose I'm saying xm, where xm has x1m, x2m. This is not power, this is just a notation, x and m. Since I was having r and n coordinates, so that's why I wrote like this. xm is equal to x1n, x2m up to xnm. So everybody will be in terms of m. So let us have some example. Say xm maybe is equal to 1 comma minus 1 raised to m, something like this. So this is in R2, sequence is in R2. If I take in R3, then you can take it as 2 by m and 4 plus 1 by m and say minus 6m upon 2m square, something like this. So this is sequence in R3 and similarly R4. Okay, so now the main task is to ask when does a sequence converge. Convergence of a sequence in Rn. Okay, so how do we define the definition? That is, let us start. Let xm be a sequence in Rn, and let E a point belongs to Rn. Then the sequence xm is said to converge E. Converge E if, can you tell me, if, what was the condition? For all epsilon positive, yes, there exists m naught belongs to natural number such that norm of x minus e that is less than epsilon. Oh, I'm sorry, actually I should write there exists m satisfying this, that is for all m greater than equal to m naught, it is satisfying this condition, that is for all, that is xm minus e that is less than epsilon. So this is definition, close bracket, bracket, bracket. What, how many brackets? 1 2 3, yeah. So this is the definition. If I write in the format of Burton book, then I will write like this: for all epsilon positive, there exists m naught belongs to natural number such that mod of xm minus x e that is less than epsilon whenever or for all m greater than equal to m naught, something like this. So both the thing are same, equivalent. This seems good. You'll see this type of definition in the real analysis by S. Kumaresan, and this in any other book they will be mentioning like this. And this one is quite nice because once you go for taking negation of this, then it will be quite helpful for you. You have to take negation of this statement like this. Here you will get confused. Okay, so this is the definition same पहले जैसा ही है, कुछ अलग नहीं है अपना, correct? For all epsilon positive, there exists m naught belongs to natural number such that do you remember the changes is यहाँ पे पहले mod था, now we are having norm because we have defined distance को हम लोग ने norm से define किया है, correct? Yeah, so this is the definition. Okay, so now the next part is the theorem. First theorem which I think शायद मैंने वहीं तक कराया था in the semester, then we moved to the Riemann integration part. Yeah, let xm be a sequence in Rn given by xm को डिनोट कैसे किया हम लोग ने, xm को हम लोग ने लिखा कैसे है, x1m x2m, this is just notation, you understand this, for using proof, for proving we are just defining like this. Okay, this is your xm, then xm is convergent in Rn if and only if for each of the coordinates sequence, that means x1 x2, or I will say xi of m is convergent in R. That means what, you are changing your convergence in Rn by convergent in R, by saying if each of these, the first one, second one, everybody is convergent, then you will say xm is convergent. This is what you have to prove, and it is if and only if. Okay, so we shall start. कहाँ से start करें बोलो? Shall we start from this one to this, or this one to this, whatever you want, tell me. Let us go from the flow only. Consider this and prove this. That will be quite easy, easiest one. Correct? So let us start. Suppose xm is convergent in Rn. Convergent in Rn. Okay. So by the definition, first of all, write E as E1, E2 up to En. Then what is to prove? To prove each xi of m. So if I am taking xi, that converts to ai. This is what I want to prove, correct? For all I belongs to natural number. No, for all I up to n. It is only up to n. Correct? So let us write the definition of this. How do we define xm is convergent? Let epsilon is positive be given. There exists m naught belongs to natural number such that, what is the condition? Norm of xm minus e, that is less than epsilon, for all m greater than equal to m naught. Correct? This is what the definition is. Now observe something. How does this norm defined? Since you know the coordinate of xm, or I'll write here, that is x1 m, x2 m, xn m, yes, minus e1, e2 up to en, and this is norm, and that is less than epsilon. Correct? This is what you are having, and how you know how to define this part, that is square root, it is x1m minus e1 the whole square plus x2m minus e2 dot dot dot. The last one is, remember one thing, ये power मतलब ये raised to नहीं है, it is just a notation, that is x nm minus en the whole square, that is less than epsilon. What do you mean by this? Can I write this thing? That means, can I write this mod of xi m minus ai, that is less than the whole thing? Do you agree? Or if you don't like this, then you can write this as square root of xim. We have used this in the last lecture, I think, minus ei the whole square, and this part, this is less than equal to द सेम थिंग ये जो हम लोग ने लिखा है दैट इज समेशन के फॉर्म में लिखता हूँ मैं summation this is xi raised to m minus ei the whole square I is running from 1 to n and which is less than epsilon. That means what? This xi mod of xi m minus ei that is less than epsilon. And what was the condition? For all m greater than equal to m naught. So what is the conclusion? In real case we just want mod, correct? So what is my conclusion here? That means your xim converges to ai. So we proved the first one. Hence proved. Let us go back to the proof once again and see. It is just simple working with inequalities. At epsilon positive there exists m naught belongs to natural number such that this is the condition. This is given to us and I just wrote this thing. इसको थोड़ा expand किया and you see this one. Correct? And the condition is for all m greater than equal to m naught. Now what I am using, I just have to prove this, that is xim is converged to ai. So I am considering this. You can write here as consider xim minus ai, which can be written as square root of xi raised to xim minus ai the whole square, and this part is less than equal to square root of this summation, and the whole thing is less than epsilon. So you are having xi raised to m minus ai less than epsilon for the same m naught. So I don't have to change that m naught, and that's it. Hence xim converges to ai, hence proved for all I. Correct? For all I up to n. 1 to n, yes. Okay, now conversely, what is the thing, what you have to assume? Suppose your each xi m a, actually m को भी bracket देना चाहिए, you just understand. Yes, to prove this this xm converges to a, this is what you want to prove, correct? So you are given with this, so let us use the definition. Okay, so xim converges to ai, that means what is the definition? For all epsilon positive there exists, see I am putting ai na, so my m naught will depend on I, so I'll write it as there exists mi belongs to natural numbers such that mod of xim minus ei that is less than epsilon. I'll choose epsilon by root n, you'll see later on ये root n क्यों लिया, for all m greater than equal to m naught, sorry mi. Yes, now this is true for each I, that means how many mi will I have? I will be having m1 m2 m3 up to mi, correct? Up to mn actually. So total I will be having mn, so I want to use everything together, so which m should I choose? That means we should choose a m naught such that everybody should be true in that region. Which m naught should I choose? Yes, this type of thing we have done in the algebra of sequences. If you are having two thing m1 and m2 रहता है वहाँ पे, तो in that case if I talk about m naught and something else, then what you have to choose? You have to choose the maximum of the both, correct? Maximum of m1 m2 up to mn. Yes, if you choose maximum, that means what? Same thing, that is for all for I equal to 1 2 up to n, you are having xi raised to m minus ei that is less than epsilon by root n for all m greater than equal to m naught. Earlier this was mi, now I have fixed an m naught which is true for all i's, i1 1 2 3 कोई भी लिया, then it is true, correct? Now if I take square of this, then means xim minus ei the whole square that will be less than epsilon square upon n, correct? Yes, Now the next part is consideration part. Consider, what do you have to consider? Norm of xm minus a, xm minus e. How does that defined? That is defined in this form, that is x1m minus e1 the whole square plus x2m minus e2 the whole square, so on up to xnm minus en the whole square, correct? And if you observe each of this term, they are less than epsilon square by n, correct? So can I write like this? This is less than square root of, this is epsilon square by n plus epsilon square by n up to, do you see यहाँ पे रूट n का यूज़ क्या हुआ? Since we were doing epsilon square, ये स्क्वायर होने वाला था, that's why. Now what? This is same as 1 2 3 up to, there are n terms, so it will be is equal to epsilon. So what do we get? We are getting norm of xm minus e, that is less than epsilon for all m greater than equal to m naught. That implies xm converges to a. Yes, do you agree? Look at the proof once again. So let us go back to the proof once again. In the first case, we are given xm convergent and you have to prove each xi is convergent. In the second case, we are starting with each xim is convergent to ai. We have to prove xm convergent, correct? So how will you prove that? So to prove this thing, you will start with the definition xim converges to ei. Then by the definition, for all epsilon positive, there exists mi belongs to natural number such that this is true for all m greater than equal to mi. Correct? Now you are having n mi's, m1, m2, m3 up to mn. You have to choose one which is true for everybody. So you have to choose let m not equal to maximum of this m1 m2 m3 up to mn. So once you choose m not equal to maximum, so you are having this condition, so square le lo. Now consider part kya, and that's it, we are done, correct? Yeah, okay. Now let us define bounded sequence. बाउंडेड सीक्वेंस वहाँ पे कैसे डिफाइन था? डू यू रिमेंबर? लेट एक्स एम बी अ सीक्वेंस इन आर एन, करेक्ट? द सीक्वेंस एक्स एम is said to be bounded if there exists a k positive such that norm of xm that is less than equal to k for all m belongs to natural number. Yes, then you say that sequence is bounded sequence. So this was the same, वहाँ पे भी definition same ही था. At the place of norm it was mod, that's it. बाकी सब same था. Yes. Now do you remember our next theorem of that? Every convergent sequence in Rn is bounded. Correct? So let us do that. Let us prove now. What is the theorem? Every convergent sequence in Rn is bounded. So this is what you want to prove. Do you remember वहाँ पे कैसे proof किया था? Yes, you should start with something, correct? Let xm be a convergent sequence in Rn converging to E, which is in Rn. Network issue was there. Yeah. Okay. So converging to E in Rn. So what is the definition? So you know the definition. What you should do here, you should choose, you should start with let epsilon is equal to 1 in the definition, correct? So once you choose epsilon equal to 1, write the definition. That is, there exists m naught belongs to natural number such that mod of xm minus e that is less than epsilon. Now epsilon is my 1, correct? For all m greater than equal to m naught. But what do I want? I want some condition on norm xm. So let us consider norm xm. Can I add and subtract something? Minus a plus a. Yes. So can I use now triangle inequality, that is less than equal to norm of xm minus a plus e. E is a real number. I should say norm e, since this is not a real, this is in Rn. And what is this? This guy is less than 1 and plus norm e. So everything, this is a number only, correct? So if this is a number only, what should you do? What should you do? So we have proved something, that is, this is true. You can choose this as a for all m greater than equal to m naught. Yes. Okay. Oh, I'll just repeat once again. So we are given xm converges to a, ym converges to b, xm plus ym converges to a plus b, xm minus ym, this is converges to a minus b, and this is. So equivalently, to prove this all three things, we will prove this alpha xm plus beta ym that converges to alpha a plus beta b. So we are doing it in three cases. Case 1 is if alpha and beta are non-zero, so I am starting with xm converges to a, and this is my result, correct? Ym converges to b, so I am having this thing. So sorry, I had forgot to record that thing. I'll just repeat it once. So let m naught equal to maximum of m1 and m2. So for all m greater than equal to m naught, you are having the result maximum choose here, so this is true. And later norm of this and this, you are considering this take together, and by using triangle inequality, so this is less than epsilon. So you have proved alpha xm plus beta yn converges to alpha a minus beta b. But we have proved this both alpha and beta are non-zero. What about if both are 0? Then result is obvious, because 0 sequence. What about one of them is non-zero? That means if I am taking alpha is non-zero, beta is 0, then I have to prove alpha xm converges to alpha a. So how can you prove? Since xm converges to a, so I can use for all epsilon. This is the definition, and at the place of epsilon I will be choose epsilon upon mod alpha, and by considering this you can prove it, correct? Is that clear? Yeah. So maybe in the next lecture I'll do some problems related to this. Okay. Thank you so much.